In addition to the utilities covered thus far, including scripting languages such as Perl, tools like awk, sed, and grep, there are a number of system utilities that you should be familiar with within a Red Hat Enterprise environment. In fact, these utilities are included with most, if not all, Linux distributions. And they feature everything from listing processes to viewing the available free memory. So, process listing, free memory, as well as available memory, so free/available memory. Disk utilization, which also includes the partitioning information, as well as disk usage with vmstat and process usage, and others. Let's begin by delving into some of those tools. The first is PS. PS reveals a process listing and status information. So status/listing information. When executed by default, it lists the processes of the currently logged in user to the TTY. So for example, we're logged into this TTY as a user Linux CVT. When you execute PS with no options, it returns processes that are tied to this particular TTY. For example, there's a bash shell in the TTY, and the PS process was executed. Whenever you run PS with or without options, you'll see the process ID, the connected TTY, the amount of time it's taken, CPU time, and the command that was executed. So the bash shell was executed as process ID 14,816 on sudo terminal number 2. PS was executed as process ID 16,094, again on sudo terminal number 2. And if we open another sudo terminal number 3, and execute PS, you'll see items related to sudo terminal number 3. However, oftentimes you want to get a comprehensive listing of processes that are running on the system, including their utilization and whether or not they're still running, and their process IDs and connected sudo terminals. So for that, we can extend PS as follows: PS-EF or PS-AUX. Either one will return a wealth of information regarding processes that affect all of the users on the system. So let's try PS-EF. Now PS-EF is a form which is compatible with Solaris. So if you find yourself operating between Linux and Solaris, -EF is going to work in both environments. When you scroll towards the top of the output, you'll notice that a wealth of information is returned. The UID, owner of the process, and for each process represented by a row, its owners to the left, including root for many of the processes that launch or set up the system. The PID, now as we've told you, PID number 1 belongs to the init process. The parent PID, init, is launched by the PID 0, which belongs to the system scheduler. When it was launched, whether or not it's connected to a TTY, the amount of time it's used, CPU time, and the process ID itself, the command that was executed, init, into run level number 5, so init space 5, since we are in a graphical setting. You may scroll through a list of these processes, and you'll see different ones that apply to system as well as user space items. So items that interact with the keyboard, the monitor, for run levels number 5, the various terminals, background processes, syslog, so on and so forth. Again, PS-EF gives a comprehensive view of the processes running on your system, whether they're owned by root, the currently logged in user, or other users on the system. So it dumps everything to the screen, and it takes a lot of different programs to constitute or to run or operate your Red Hat Enterprise Linux desktop environment. So here are those processes, consistent output. Now we did also mention, let's reset the buffer, that you may optionally use PS-AUX to dump information regarding processes. More information is dumped, such as the percentage of CPU, percentage of memory, but overall, basic information related to who owns the process, the PID of the process, the TTY that it's connected to if applicable, as well as the command used to execute the process, the time when it was started, and so on. So PS-AUX returns a little more information, but both EF as well as AUX return considerable information. This information is dumped as a one-off, so in order to see if new processes have been launched, you need to re-execute PS on a recurring basis, which leads us to another useful command, and that's the top command. Top combines a few useful utilities, including PS, as well as free, and uptime. So top combines PS, uptime, as well as free, and updates regularly. Let's give top a try from the shell. We'll clear screen and execute top. Top moves to the top of the list by default processes that are executing and using the most amount of CPU time, such as the GNOME terminal, which is currently using about 6% of CPU time. And because we've used the mouse to block, it shot up to over 13% of utilization. But above in the top output, you'll see uptime related information, such as how long the system's been up and running. As you can see, it's been up for 6 days. It reflects the current time, 13:58. It's been up for 6 days, 4 hours and 38 minutes. There are 3 users connected. For each TTY that's open, such as sudo terminal 1, sudo terminal 2, as well as any other connected users, they'll be represented as users. So 3 users means that there are 3 connected sessions, 2 shells in this GNOME terminal window, as well as the X window session altogether. So 3 users are connected. There's a load average return for 1, 5, and 15 minutes. Low numbers beneath 1 are usually good, which indicate that the system is currently not in heavy use. Now let's Control-Shift-T and execute uptime to show you how the output would be returned. As you can see, the time, current time that is, we can compare it using the date command. The number of days as well as hours and minutes the system has been up. Connected users, I've just opened a new shell, so there are now 4 users connected. And load averages for 1, 5, and 15 minutes. So let's just list, since we're segmenting top into multiple commands, that a third command, which provides useful information regarding system utilization, is uptime. Returns useful system utilization information, including current time, uptime, registered in days, hours, and minutes, as mentioned. In addition, the number of connected users and the load average. So connected users and load average registered in 1, 5, and 15 minute values. So uptime is only a component of top's output. So let's return to top. We'll clear screen, and our second shell should have a top instance running. In addition to uptime information, we also see information regarding CPU utilization as well as memory utilization. Let's zero in on memory utilization. We see that there's a total amount of memory available to the system, which is around 512 megabytes. This is about half a gig worth of memory that's available to the system, of which about 500 megabytes, or about the whole half a gig, is used, with barely 88 megabytes free. Or in this case, 8,000, so 8 megabytes, just barely over 8 megabytes free, 8,816 K free. The number of buffers, swap space, if you recall we set up a gig of swap. How much of swap is used? You always look at top to see if a large amount of swap is used. 92K of a whole gigabyte is very little, which tells us the system is doing most of its work in random access memory. Of course, the more users who connect to the system and run applications, the more taxing the processes would be on system resources, resulting in degraded performance unless we upgrade the system's components, memory being one of the most important, if not the most important component in system performance. The amount of swap free, almost the entire gig is free. So whenever you're looking at TOPS output or freeze output, you are looking to see how much of swap is in use, how much of random access memory is in use. The memrow represents random access memory. So again, that leads us to the next tool, free. Returns memory utilization. And it returns also swap information. So it includes random access memory as well as swap information. You must pay attention to these statistics to have a sense from time to time of how your system's performing or underperforming. And again, TOP organizes its process information similar to the way PS returns its output by arranging the most used or frequently used programs at the top of the list. So we should also just make sure to mention that TOP does indeed include PS information. TOP can be refreshed. You may also edit the interface. You may also type H for help, where you'll see all sorts of options that you can use to interact with the program, such as changing colors, toggling summaries, altering the fields and the columns, manipulating tasks. You can kill processes or renice them, for example. Renicing a process in Unix and Linux is equivalent to upgrading or downgrading the privileges in a Windows environment, the process privilege, the priority, that is, of a process. So if you renice a process with a lower priority number or a lower number, it gains higher priority, and a higher number gains lower priority. By default, programs are usually run with a zero nice level. But if you were to lower that number, let's say to -5, then a process would have a higher priority and require more system utilization or system resources, sending up the system utilization. So you can interact with processes, you can find something to kill like a shell, but we'll refrain from doing so that we don't kill our existing session. And this interface is updated all the time. Again, H for help, and you'll see information regarding how you can interact with the interface. Super. So that's a TOP command. Now, there are other utilities. We did mention that free is available. Let's show you how free is executed. Execute free with no options. It returns all of its output in kilobytes, including random access memory and swap information. If you execute free with the -M option, then the information is returned using human-readable format, which usually returns megabytes. So execute free for human with the -M option, readable format, which usually returns output using megabytes and optionally gigabytes. Now yet still other commands. For example, a fifth useful system utilization command is df. df returns disk partition information, partition/mount point information. And a default usage or application of df would be as follows. df with no options returns info using kilobytes, whereas df with the -H option returns info using megabytes /human readable, which will return gigabytes and terabytes if necessary. So gigs, tera, etc. That's what's meant by human readable format. So let's return to the shell and execute a df. Again, df dumps your file systems to the screen, and it indicates usage information. So here we see on this particular enterprise system a logical volume, its size, as well as a boot partition, which is not a part of the logical volume set, which is tied to HDA1. When we rerun this with df-h, you'll see that human readable is returned. So this tells us that the logical volume is 35 gigabytes, of which 2.7 is in use, which means the bulk of the Red Hat Enterprise installation occupies the 2.7 gigabytes. with 31 free, the percentage in use, so we have 92% of the root file system free, and where this storage space is mounted. In this case, dev mapper vol group 00, logical volume 00 is mounted to the root file system. And here are its attributes. Ditto for dev HDA1. It is about 100 megabytes, of which 11 megabytes are in use, which includes, of course, the kernel, the initial RAM disk, and so on, of which 84 megabytes are available, which results in 12% utilization, which means we've got roughly 88% free on this mount point for updated kernels and other items. And there's a tempfs, which is 252 megabytes. All of it's available and can be used for storing information in memory. Tempfs file systems are in-memory file systems. Well, again, DF returns the file system and mount point information plus some statistical information regarding the utilization of your storage. So when you log on to any Linux system, and for that matter any Unix system, you can execute DF. But on any Linux system, you will be able to execute df-h to quickly and in a human-readable format get a sense for the mounted file systems. This also includes if you've briefly mounted a CD or DVD drive. It'll appear in the list of mounted items as well. Now let's move on. We still have other system utilization utilities to discuss, including vmstat. vmstat reports on processes, memory, paging, block I/O, and that's block input-output, traps, as well as CPU activity. If you need raw numbers on how your memory, CPU, and disk storage systems are performing, you'll get the bulk of it from vmstat. Now if you go ahead and execute vmstat, general usage, or simply vmstat, you'll see that it returns momentarily information regarding your swap, as well as your memory, as well as your I/O, input and output, bytes in, bytes out, system utilization, and CPU utilization. So you get everything from processes through CPU utilization. And these numbers are all sensible values registered in kilobytes. If you remember, when we executed free before, we saw that 92 kilobytes of swap were in use. Well, vmstat tells you that up front. There we see swap drive utilization is 92 kilobytes. We also see the amount of free memory. At the time when we executed vmstat, about 7 megabytes were free. When we executed the free command, about 7.2 megabytes were free, roughly. And how the information is broken out into buffers and cache, swapping in, swapping out, bytes in, bytes out for I/O. The swaps in and out should be low, indicating that not too much I/O is being generated in and out of your hard drive's swap partition. System requests in, as well as user processes and system processes, as well as CPU information such as how many waits, how many are outstanding, so on and so forth. vmstat makes that available information really easy to parse, even with third-party programs. vmstat can also report on hard drives or partitions. For example, vmstat-p followed by dev HDA1 will return partition statistics on dev HDA1. So it returns partition stats for dev HDA1, which is our /boot mount point. If you recall from our df dump, df-h, HDA1 represents the boot file system. From this you'll get information regarding reads and writes, as well as requested writes. This is important information. You need to have a sense for how many reads and writes are operating on your system, what's normal and what's abnormal. This is a very low number of reads, by the way, just over 1,000, and an extremely low number of writes, which indicates our system is not in heavy usage. If we were in heavy usage, we'd see hundreds to thousands of writes, we'd also see perhaps hundreds of requested writes. And if our system were functioning more like a read-only file server, we'd see possibly tens of thousands of reads, perhaps because of the traffic related to sharing the data on the hard drive. So VMstat can zero in on specific hard drive partitions on your system. Now there are GUI tools for those of you accustomed to the GUI, let's say from Windows or other Unices. And a useful utility is GNOME System Monitor, which combines all of the information that we've been talking about thus far in a useful interface. So this is a GUI combining most system utilities. But you don't always have GUI access to a Linux system. Your chances are more likely have access to the shell, which means you need to know how to quickly tell how much memory is in use, which includes how much swap memory is in use, which processes are taking over or owning your system, as well as how the disks are being used, the partitions. Well, let's take a look at GNOME System Monitor. We'll execute a which GNOME, and again, tab completion can be used. System Monitor. This tells us it's in user bin, which means that it's basically available to all users of the system. Let's execute it using tab completion. If you execute GNOME-system, you'll see that there's another utility, the log utility. We're interested in the monitor utility, which will pop up. Notice a check for SE Linux was made, but on this Red Hat system it's not enabled. We like to look at GNOME System Monitor because it provides very useful information in an easy-to-follow graphical interface. GNOME System Monitor gets its information from the same sources as do other utilities such as top, df, free, ps, and others. It simply provides the information graphically. So here we see CPU utilization from 0 to 100%. Right now we're somewhere in the 1/3 percentage range of utilization. And we see the colorization of the graph for CPU utilization. If you click on the link, as I've just done, you can change the color to be anything else, or place your hex code in to indicate a different color for the graph. We also see user memory and how much has been swapped. So we see swap utilization, 92K, as well as random access memory. User memory is roughly 197 or 200 of the 500 megabytes, but we do know that the system is using the bulk of the 500 megabytes because we use the free command. This graphical interface is reporting on user memory utilization, which means of the 502 megabytes, about 300 are being used by the Linux operating system, and 197, which includes the GUI that we're using and other programs like the GNOME system shell or the GNOME terminal and other programs that are running in the GUI environment, such as the panel, the top and bottom panel, the GUI, so on and so forth, and the other Control-Alt consoles that are available. Here's network utilization. How many received, how many sent per second. If you're connected at a gig, this should give you a perspective regarding gig, and ditto for 100 megabits per second. Navigate over to processes. You see what you see in top as well as in PS. The name of the process, it's organized a little differently or slightly differently. The name of the process, current status, percentage of CPU, nice level, which defaults to 0 for most programs, the process ID, and how much memory the process is currently using. You can also sort by any of the columns. So you want to see nice levels that are above or below, just sort ascending or descending. Percent CPU utilization, if you want to see most active to least active. In this case, we sort descending, and we see that GNOME System Monitor is using the bulk of the system's resources. Status, you can sort running versus sleeping. So as we can see, most programs, except for netstat and XRDB, which have been zombied, are sleeping, while a few are running or in the running state. Nautilus is the file manager within GNOME. So again, you can sort by anything that you like, any of these column headers. You may also manipulate the column headers that are present in this environment. Navigate to Preferences and change those process fields. So if you want to see the user who's responsible for a process, go ahead and click on User, and now you'll see the user. Additionally, you can rearrange the column headers, like I've just moved user here, and we can also sort by user. So for example, Linux CBT is responsible for X number of processes, whereas if we scroll down, we'll see what root's responsible for. Normally, when you run the GNOME System Monitor utility, as a non-privileged user as we have, you only see processes that are related to the currently logged in user. That's something that you should keep in mind. Go to View, and it says My Processes. If you want to see active processes, only items that are currently active, such as GNOME System Monitor, view active processes, and right now only GNOME System Monitor is running. Actively, that is. We see uptime information. The load averages for 1, 5, and 15 minutes. Of course, it's been more busy in the last 1 minute because we've been running GNOME System Monitor. If you want to see all processes, which includes system-started processes such as init, then by all means do so. And if you sort by ID, you'll see that process ID number 1 belongs to init. In this case, it was the first process to set up this environment. You can elect to try to stop the process, but an error will be thrown because we're not logged in as root. You can continue it, end it, kill it, change its priority, hide the process, open files, see the open files by the process, and so on. So through View, you can control what you see. You can also elect to list dependencies to see what the dependencies are between a process and its children. So kthread, for example, is responsible for the list of processes you just saw. Audit ID, or audit D that is responsible for running a Python instance. So you can see a hierarchy, a dependency list of processes. You can even hide them, so on and so forth. So there's all sorts of information. There's help, change your preferences to change the columns. You can refresh whenever you like. Just navigate up to the appropriate option, and you'll be able to. If you need to kill a process, you definitely can. Find something that you actually have control over, such as a shell interface, and just right button kill, and that kills the process. And in file systems, we see what we would see normally when we execute df. devhda1, which is the boot file system. Double click on it, Nautilus brings it up, where you'll find the initial RAM disk and the kernel, amongst other things like the config file and the system map, and utilization information presented by df. We also see the logical volume, where root is mounted, as well as in Sun RPC file system, which is used for remote procedure calls. We don't see the tempfs file system, as it's used by the operating system. So GNOME System Monitor presents processes, resources in a graphical setting, as well as file system information, and you can alternate between different useful columns at different times. Now just a quick note on where these tools or utilities obtain all of this information. If you look at the contents of the proc file system, you'll see exactly where this information comes from. df-h doesn't show proc, however, grep of proc from etc fstab will reveal that it is a special file system of type proc mounted at proc. The proc file system is maintained by the Linux kernel. It's all in memory, and most of the items in this directory are of size 0 bytes. The information in the files in these directories, or in this directory, is constantly changing, such as memory utilization, the processes that are running, so on and so forth. For each process that's running, beginning with init, you'll see a directory which represents that process ID's entry. So 1, for example, represents init's environment, and here's what init is responsible for. For every program that's executed, a directory is created, and the dependencies and items related to that process ID are maintained beneath the parent process ID's directory, such as 1 for init. In addition, beneath proc, you'll see information related to all aspects of the kernel's existence, such as cryptography, command line, CPU info, disk statistics, devices, DMA, core dumps, networking information, partition information, supported file systems, and many of these files are text files which can be catenated. For example, a cat file systems tells you the file system supported by this kernel, the kernel that we're using. And here they are. sysfs all the way through ext3, ext2, AutoFS, TempFS, PipeFS, USBFS if we plug in a USB stick, and so on. If you ever want to know the processor types on your system, there's a file named CPU info. Cat the contents of CPU info, and what's enumerated represents the details of the processor connected to your system. This instance of Red Hat Enterprise is installed on an older Celeron processor, which is a gigahertz in speed. It's stepping, and all the details that were ascertained from the processor are displayed on the screen. It's the first processor indexed at 0. It's an Intel processor, the CPU family and model, the fact that it's a copper-mined Celeron processor, and it's a gigahertz with 128 cache. And here are the features, floating point, so on and so forth, supported by this processor. So CPU info will tell you the CPU is connected to your system, one or more, indexed at 0, of course. And again, as mentioned, there is a net subdirectory which means network information related to the protocol supported by the build of the kernel, including IPv4 as well as IPv6. You can take a look at that information. You can change it. In fact, when we use syscontrol later on, you'll see that really what utility does is changes some of the entries in the proc file system. So in other words, you can influence a lot of your system's behavior by updating manually or using the appropriate utility entries beneath the proc file system. Of course, unless you're an expert or you use specific files beneath proc, you shouldn't modify them directly. You should use the abstracted tools to modify them, such as netstat for the routes, for example, because as we see, there's a route file. If we cat the contents of route, it returns what we would see if we were to dump our routing table. And there's other IPv4, IPv6 information. Here's an IPv6 route file. Here's information related to the group messaging protocol for 6 as well as the group messaging protocol for version 4 of IP. You'll find that anything that relates to IPv6 has 6 somewhere in the name of the document. There's a subdirectory for netfilter, which is the IP table's built-in firewall. And all sorts of other useful information. TCP statistics, socket statistics, these are all the TCP connections that are in place. Netstat simply reads this information and displays it to us in a nice format. So beneath the proc file system is all sorts of useful information. We've just touched on some of the basics, such as the CPU info, etc. This command line file we just catted simply stores where the root file system was launched from. Root was launched from dev vol group 00 launch volume 00, indicating that when the system came up, it created its root out of that particular device. But again, many of the options are here that vmstat, netstat, and many other programs rely upon for displaying to you. Most of the items are 0 bytes because they're updated dynamically by the kernel, and they're accessible to most users on the system. But only root can make changes to items that are in this particular directory hierarchy. Now there are other utilities, such as kill. If there's a program that you'd like to kill, you can just execute kill followed by the PID. We'll just list it and we'll use it later on in our studies. So for example, we'll just include as examples for the proc file system that we've catted or catenated proc CPU info as an example. Kill, PID, kills the process with a given PID as an example. So it's a shortcut rather than launching GNOME System Monitor to terminate a process. Another useful utility is the run level utility, which we've mentioned during installation. It returns 2 columns, left and right. The first column, or first and second, first column tells you the previous run level. Second column tells you the current run level. So it returns run level information using 2 fields. The first represents previous run level. As you know, as we've mentioned, you can execute init at any time to alternate between run levels. So you know which run level you're in by focusing in on the second field. You also know if your system was previously in a run level if anything other than N is displayed. N is a shortcut for not applicable. In other words, this means the system was booted directly into run level number 5. But if we were to navigate to run level 3, then return to 5, this N would be changed to 3, and then the 5 would reflect as 5, indicating we went from 3 to 5. Or, if we navigate to 3, then we'll see 5, then 3 for current, and so on. So again, just to recap, there's some key utilities that can help you to ascertain statistical information from a Linux system. PS lists process information. You run it with the -EF or AUX options, but you can optionally run it with a specific user, such as PS-U root, to return processes owned by the user root. Free, run with the free-M option for human readable output, returns the breakdown of memory utilization, including random access memory and swap information. DF returns your partition information, which includes statistical information for each mount point. VMstat reports on pretty much all of the above: processes, memory, paging, so on and so forth. Top combines the output of PS uptime as well as free and makes it available in one neat interface that's updated frequently. GNOME System Monitor, or GNOME-System-Monitor, is a graphical utility which displays most of the information found in top in a nice, concise interface which is updated frequently. You can cat the contents of many of the text files beneath the proc file system, as it's a dynamically maintained file system maintained by the kernel. You can kill processes using kill followed by the ID. For example, since we haven't done so, let's take a brief look at this window. By executing PS with no options, we see that the bash shell here is 16160. So from a separate shell, if we were to kill, and we'll just kill, here we press K to kill, we can kill from top, so we'll kill 16160. This will kill that extra shell that has a bash window open, if that's indeed the process ID. And let's just take a look here. We'll PS, and we'll try to kill 16160 to kill the bash instance. Then we'll PS EF grep 16160. And we see that the bash instance is still running. And it could be set to respawn, which could explain why it's still open. But nonetheless, generally under normal circumstances, the kill would kill that particular bash shell or the process ID referenced by the kill command. So these are just some of the commands that will make you more proficient at navigating a standard Linux system. Now we're going to move on to some other things that you can do inside your Linux environment.